Welcome to the second video of the Fortitudo.tech Python package walkthrough. In this video, we'll go through a simple example using CVaR and entropy pooling on a log normal multi-asset P&L simulation. So we start at the front page of the repository and then navigate to examples. And then we see that the first example we have is called mean CVaR and entropy pooling, and this is the one that we'll be going through. When you load the example, the first thing you see is just a description of what it is about and some useful references to build deeper understanding of the methods. In the first code cell, you can see that in the same way that we have a package called numpy, pandas, and seaborn, we also have a package called fortitudo.tech that we import as ft. So every time you see something with an ft in front, then you know this is something coming from the Fortitudo.tech package. The first function that we use is called load P&L, and this is basically to load this P&L simulation that follows with the package. Next, we compute some statistics using the function called simulation moments. So here you can see we get an overview of the mean, the volatility, skewness, and kurtosis. After that, we want to specify the portfolio constraints that we have and a prior probability vector. So you can see that initially we have this matrix G and vector H that specifies some individual upper or lower bounds. First, you see that we have individual upper bounds of 25%, and this imposes some diversification in the portfolio by requiring at least 4 assets to be invested in. And then we have a lower bound of zeros. So this is a long-only portfolio. After that, we specify a prior probability vector, which in this case is just uniform. If you wanted to do something else, as for example exponential decay, something like that, you could also do it. By default, if you don't specify a probability vector, it will assume that it has these values. So this is just to illustrate to you how you use it in the mean CVaR optimization object. Okay, so now we want to initialize the mean CVaR optimization object, and the first thing we do here is to extract the values of this pandas data frame from the P&L and put it into a numpy array instead, because this is the input that the mean CVaR class requires here. In addition to that, we input the inequality constraints and we add this prior probability vector. After doing that, we can immediately compute efficient portfolios. So here we use the efficient portfolio method. If we don't specify any return targets, it will just return the lowest risk portfolio for us. If we specify a return target as we do in this case, then it will require that the return is at least these 5%. An important note about the mean CVaR class is that by default the optimization is performed with demeaned portfolio P&L when you compute CVaR. And this is something that we give arguments for in this article that is called Variance for Intuition, CVaR for Optimization, where basically we go through the pros and cons of using variance and CVaR and compare the two risk measures. And give the argument for that if you want to have a nice separation between risk and return for the CVaR risk measure, then you must use it with the mean P&L. Okay, so in this example here where you see that FT CVaR options, this is just to show you how you can deactivate it. So if you want to do CVaR optimization including the mean, then you can still do it, but this is not what we recommend. This is just to show you how to play around with the options. Okay, so now we have performed some efficient portfolio optimization with the prior probability distribution. And now we want to add some entropy pooling views to that and then optimize our portfolios again. So here in this example, we assume that we have made some analysis and concluded that the expected return on private equity should be 10%, while the volatility should be at least 33%. How we arrived at this conclusion, that's of course entirely up to you. And this is just to illustrate how to use this functionality with views on means and volatilities. So here, if you want to implement an entropy pooling view on the expected return of some asset, then you just use the column of that asset and transpose it into a row. If you want to implement a variance view, well, then it will be the returns of the asset minus the expected return of that asset squared. And here it's important to note that we already subtract the 10% that we will have in the view. Because if we subtract the old prior mean here, then it will create a logical inconsistency in the variance view and the expected return view. So this is an important first realization that you have to make when you implement entropy pooling variance views. Alright, so now to finalize the constraints for entropy pooling, we of course require that all our probabilities they sum to 1, so this is the first thing, and then we have that the expected return row for the private equity must be equal to 10%. Finally, we have this inequality constraint where we just take the variance row and implement an upper bound that the volatility should be at least 33%. Once we have specified all these things, we can just call the entropy pooling function, which will return the posterior probability vector for us. So the first thing we want to do with the posterior probability vector at hand is to examine if our views have been implemented correctly. So what we see here is that for private equity, the expected return is 10% and the volatility is 33%. So it seems that the views have been implemented correctly. It's also interesting to analyze what have happened with the other assets. So we can see that we have decreased the expected return of private equity, but what has happened with DM equity and EM equity returns? To see this, we can scroll up to the prior simulation, where first we can see that private equity had an expected return of 13.7% before, but after we implement the view, then the expected returns on all the risky assets came down while the expected risk increased. And this is one of the things that entropy pooling does for us to implement views in a way that imposes the least amount of spurious structure. So this is really why it is powerful. Okay. Another way to examine your entropy pooling views is simply by plotting the P&L distributions with the prior and the posterior, just to see how it looks compared to what it was before. So if you have implemented something which is very, very extreme for the Monte Carlo simulation that you input to entropy pooling, you will be able to see it quite immediately here. In this case, it looks okay. We can see that there's a decrease in the expected return and that the volatility has increased. Alright, so now we want to perform the optimization analysis again, but just using the posterior probabilities in this case. So here we initialize another CVaR class where we use the same P&L simulation, the same constraints, but now we specify the probability vector to be the posterior instead. And then again, we can optimize our portfolios using the efficient portfolio method for the minimum risk portfolio, and again with a return target here. So in the next cells, we just compare the prior optimization and the posterior optimization. And this is for the minimum risk portfolio. So in this case, what we can see that when we increase the risk of the most risky assets, then the posterior optimization for the minimum risk will allocate less to the risky assets that we have in the investment universe. So this makes quite good sense. When we look at the optimization with the return target, then we see that since we decreased the expected returns of the risky assets, we now must allocate more to them to be able to achieve an expected return of 5% for the portfolio. So this also makes quite good sense. All right. So far we have just been optimizing for one single portfolio. But we could of course also optimize efficient frontiers. So here we use the efficient frontier method, and yeah, by default it will use 9 portfolios to span the efficient frontier. After doing that, we compute the risk of the portfolio. So here we use the functions portfolio vol, portfolio var, and portfolio CVaR. Yes, and we do the same thing for the posterior optimization, but now when we compute the risk, then we use the posterior probability vectors, Q instead of P. And then we collect it in one data frame and look at the results. So here you can see that this portfolio with index 0, this is the minimum risk portfolio, and the portfolio with index 8 will be the highest risk portfolio. So this is also what you see here when you compute the risk that is increasing. The same thing, we do it for the posterior, and here, yeah, you can see that there's of course some differences in how the efficient frontiers look, but also you note that the risk in general for the highest risk portfolios also increases, which also makes sense because we just increased the volatility of all the risky assets that we can invest in here. Okay, so this is the end of the first example, and as always, if you want to squeeze out that last performance from this code, then you should give the repository a star and tell your friends, and then I hope to see you in the next video.